Graphical method in linear programming is suitable for the problems consisting A. 4 variables, B. 3 variables, C. 2 variables, D. 5 variables. Before selecting the correct answer, let us introduce with the nature of the graphical method. The graphical method in linear programming is suitable for problem consisting of 2 variables. This is because graphical solution involves plotting constraints and objective function on a 2-dimensional graph, which only visible with variables. For problems with more than 2 variables, graphical representation becomes impractical, and other methods like simplex are used. The graphical method provides a visual approach for finding visible regions and optimal solutions for linear programming problem with 2 variables. That's why the correct answer is number C, 2 variables. Because each graph consists of 2 axes. In linear programming problem, the visible region, so the definition of the visible region is the set of all solutions that satisfy the constraints equation but not necessarily the non-negativity restriction. B. Consists of only the boundary lines formed by the constraints. Is defined by the intersection of all the constraints inequalities and non-negativity condition. D. Represents all possible values that satisfy the objectives function. Explanation. In linear programming, the visible region represents all possible solutions that satisfy all the constraints of the problem, including both the inequality constraint and non-negativity restriction. The objective is to find the optimal solution with the visible region. A linear programming problem typically involves an objective function that needs to be maximized or minimized subject to a set of constraints. These constraints are usually inequalities, and they define a region in the solution space where all the constraints are satisfied. This region is known as the visible region. Accordingly, the correct answer is number C. Visible region is defined by the intersection of all constraints, inequalities, and non-negativity condition. Consider the following statements in respect of PERT, Program Evaluation and Review Technique, and CBM, Critical Path Method, and state which of them is correct. PERT is event oriented while CBM is deterministic. PERT is probabilistic while CBM is deterministic. Leveling and smoothing are the techniques related to resources scheduling in CBM. A. 1 and 2 1, 2 and 3. B. 1 and 2 only. C. 2 and 3 only. D. 1 and 3 only. Explanation. A project can be defined as a combination of interrelated activities which must be executed in a certain order before the entire task can be completed. PERT, Program Evaluation and Review Technique, takes account of uncertainties or certainties. So it is a probabilistic. And CBM, critical path method, involves the critical path in the network from starting to ending event and defines the minimum time required to complete, so it is deterministic. Both of them are used for planning and scheduling with leveling and smoothing technique. So the correct answer A. 1, 2, and 3. If there are m sources and n destination in a transportation matrix, the total number of basic variables in a basic visible solution is a m plus n, b m plus n plus 1, c m plus n minus 1, d m. If total demand equal total supply, then it is a balanced transportation problem. Otherwise, it is called unbalanced transportation problem. The objective of transportation problem is to maximize profit, minimize cost, minimize profit, or maximizing losses. The correct answer for question 4 is C, m plus n minus 1, and the correct answer for question 5 is A and C, maximizing profit or B, minimize cost. A and B. The correct answer is A and B. First example, solve the following LPP using penalty, big M method. Okay. Given min z equal 20x1 plus 30x2 plus 16x3. This is an objective function concerned with the problem of minimization. $20 is the coefficient of x1, refers to the cost of 1 unit of x1. 30 is the coefficient of x2, points the coefficient points the cost of 1 unit of x2, and 16 is the coefficient of x3. This objective function is the subject to 2.5x1 plus 3x2 plus x3 more or equal 3, and the second constraint is x1 plus 3x2 plus 2x3 more or equal 4. The non-negativity condition is x1, x2, x3 more or equal 0. So the givens are 2. The objective function is minimization function. Very good. Number 2, the corresponding constraints are suitable. The two constraints are more or equal. what is the first step here is to convert inequalities or constraint into the standard form by subtracting surplus or slack variable s and adding artificial variables a. A is more or equal 0, not equal 0, actually more than 0. Now the new constraints will take the following shapes: 2.5x1 plus 3x2 plus x3 negative s1, s1 is the slack variable, plus a1, the first artificial variables, equal 3. The second constraint is x1 plus 3x2 plus 2x3 negative s2 plus a2 less or equal 4. 3 and 4 are constants. 2.5, 3, 1, 1, negative 1 and 1. These are the coefficients of variables of constraint 1. Then 1, 3, 2, negative 1, positive 1 are the coefficients of the second constraint, equal 4. 4 is the constant here. Let's see the next slide. To the second step, we are matrixing between brackets. We are matrixing the equations. This is a form of matrix. Let's look. 2.5, 3, 1, negative 1, 0, 1, 0. These are coefficients of constraint 1. 1, 3, 2, 0, negative 1, 0, 1. These are the coefficients of constraint 2. x1, x2, s1, x3, s1, s2, a1, a2. These are variables. And 3, 4 is constants. These are constants. Step 3, to convert z or objective function to zero equation. So to take the terms from the right side to the left side, and we capture that. We capture z negative 20 x1, negative 30 x2, negative 16 x3 plus 0 s1 plus 0 s2 minus ma1 minus ma2 equal 0. Now the first steps is to design the primal table. Primal table consists of 4 rows and 9 columns. The upper row represents the non-basic variable. Non-basic variable x1, x2, x3. The cells inside the cells for the row 1 are the coefficients of the constraint 1, while the cells for the row 2 are the coefficients of the constraint 2. So 2.5 is the coefficient of x1 in the constraint 1. Respectively, 3 is the coefficient of x2, 1 is the coefficient of x3, negative 1 is the coefficient of s1. Constraint A has no s2 and has no a2. That's why it's 0 0. 1 is the coefficient or parameter of a1 in the constraint 1. So also 1 is the coefficient of x 1 constraint 2, 3 2 0, negative 1 0 1 4 respectively. Negative 30, negative 20, negative 30, negative 16 0 0. Negative m are the coefficients of z. Check z, the zero equation of z, or the zero equation of objective function. Remark, the coefficients of the objective function are negative and the coefficients of the artificial variables are negative and big. That's why it's called big M. The deletion of the negativity is required to find the optimal solution. To solve the mentioned problem, we need to apply the following formula. What that mean? If we are planning to find the optimal decision, the negative value in the row 3 must disappear. To disappear these values, the negative value in the row 3, we need to apply the following formula. Okay, the mentioned formula in the previous slide states that m multiplied by between brackets r1 plus r2 plus r3. This multiplication r1 plus r2 brackets multiplied by m plus r3. Now we are going to apply this formula vertically, looking at the table, primary table, vertically. So 2.5 is the coefficient of x1, where in the row 1, and 1 also is the coefficient of x1 but in the row 2. R3 is lower row. So these figures 2.5, 1, negative 20 are coefficients of x1. All of them are the coefficients of x1. The result would be 3.5 m negative 20. 3.5 is 7 over 2. So is 7 m over 2 negative 20. M times 3.3 negative 30, it is 6m negative 30. and 3m negative 16 m multiplied by brackets negative 1 plus 0, it is negative m. M multiplied by 0 negative 1 plus 0, it is negative m. M multiplied by 1 plus minus 1 is 0. M multiplied by 1 plus minus m is 0. The last is m multiplied by 7 plus 4 is 7m plus 0 is a 7m. So now we applied this formula in order to escape the high negativity of the values in the row 3. Now the second step is to assume very big number for m. Very big number for m. Why very big number for m? Because our aim to change the negativity of the values of that to positivity with the high coefficients. This is our target. Let's see our harvest in the next slide. Table 2. We copied the result of the previous formula and we pasted it here. Okay, 7m over 2 negative 20, 6m negative 30, 3m negative 16, negative m double 0, and 7m. So now we are going to apply the main steps. Okay, first, to determine the entering variable, we need to assume biggest, very big number for m and let it be 100. We assume that m equal 100, and to find the positive value, to convert this negative value to what? To positive value. So 7 times 100 over 2 negative 20 is 330. So that's correct. Let's move to the second column x2. 6 times 100 negative 30, the remain is 520. And the last here we are focusing on the basic variables, non-basic variables in this case, x1, x2 and x3. S1 and S2, A1 and A2 are artificial or slack variables. Don't worry. So 3 times 100 negative 16 equal 284. So the biggest positive value is 520, which faces x2. Then x2 is an entering variable. In case of minimization, the entering variable, the key variable, the entering column, that variable which faces biggest figure, the biggest number in the row 3. row 3 or row Z. We use, so x2 is set to be entering variable because it faces biggest figure in the row 3 equal 520. We found, actually we determined entering variable. We have the formula which mentioned before, m r1 plus r2 between brackets plus r3. D'accord? Second step is to point the leaving row. So to point the leaving row, just look to the column of constants, cons, and the column of x2 or entering variable. Divide the column of constants over the column of x2 and find the least result of this operation. Then point where the least result has happened. Okay, check. 3/3 equal 1 ratio mine, and 4/3 equal 1.3. Equal 1.3. So RO1 is said to be leaving variables because it got least ratio of division. So then the row has the least ratio is said to be the leaving variable, which is A1. Okay? Which is A1. Then R row 1 or between brackets A1 is the leaving variable. X2 is entering variable. The intersection point between R1 and X2 is set is pivot element or key element. This 3 is the key element, intersection point between row 1 and column X2. Then in the next slide we are going to determine what, or to find the pivot equation. The pivot equation equal R1 over key or key element or pivot element. D'accord? Okay, referring to the previous table, the key or pivot element is an intersection point between row 1 or A1 and column X2, or between leaving and entering variable. This key or pivot element equal 3. To determine the key or pivot equation, this is the main equation, plays significant role in the process of finding optimal solution. To determine the key or pivot equation, we need to divide row 1 over pivot element. The coefficients of A1 or row 1 are 2.5, 3, 1, -1, 0, 1, 0, 3. This over 2. The result is given 5 over 6, 1, and 1 over 3, and negative 1 over 3, 0, 1 over 3, 0, and 1. These values will be considered as the values of x2 in the next table or instead of a1. Okay. 5. The entrance of x2 as basic variable leads to the following changes in row 2 and row 3. Row 2 and row 3. So, R1, R2, and R3, or row 1, row 3, and row 3 represent A1, A2, and Z respectively. PE stands for pivot element and PEQ stands for pivot equation. That's all. The first iteration of the problem, we need to examine the change in row 2 AO2 or the change in row 3 O3. Okay. This is the iteration. First iteration, row 2 or O2, the impact of the entrance of x2 as basic variable on A2 and Z. Okay. To check these changes, we are going to design two tables, one for A2 and the other for Z. So now how to find the new R2 or the new A2? So we need to formulate three rows. First row, the upper row for A2, the original A2, the values of A2, the coefficients of the row 2, and the second row is the pivot element of A2 multiplied by the pivot equation. Pivot equation is given, and the pivot element of A2 is the intersection point between the entering variable and A2. Okay. So we are going to copy the values of A2 as it is from the previous table and paste it here. Then we are going to find the result of multiplication. These results should be subtracted from the original A2. The new A2 is given negative 3 over 2, 0, double 1, negative 1, negative 1, 1, 1. These values should be the values of A2 in the next table. Also, we are going to do the same, to repeat the same procedure to find the new R3 or the new Z. So the first row in this operation represents the values, the original values or coefficients of row of Z, and then the next row is multiplication of the pivot element of Z by the pivot equation, and the result is given. And new Z is the result of subtraction row 1 by row 2. So we found out this negative 3 over 2 plus 5 0 m negative 6 m negative 10 negative m negative 2m plus 10 0 and m plus 30. Iteration 4. So the following steps explain the changes resulting from the entrance of x3 as basic variable in x2 and z. We are going to follow the same previous procedure to calculate the changes in x2 and z. The new x2 at the result of entrance of x3 as basic variable, and the new z at the result of the entrance of x2 as basic variable is shown. We apply the same previous procedure to find these changes. Okay, the last iteration, table 4, shown R1x1, R2x3, R3z. Looking at the last constant column, the value of x2 equal 2 over 3, the value of x3 equal 1, and z equal 36. Okay, the iteration is set to be finished. Since there is no positive coefficient in the row of z, the iteration is set to be stopped. An optimal solution is presented where x1 equal 0, there is no x1, x2 equal 2 over 3, x3 equal 1, and s1 equal s2 equal 0, a1 equal a2 equal 0, and z equal 36. Let's try to check the proof of our findings. Return back to our constraints, where the first constraint is 2.5 x1 plus 3 x2 plus x3 negative s1 plus a1. There is no x1, that means 2.5 times 0 plus 3 times 2 over 3 plus 1 plus 0 plus 0 equal 3. Correct, proved. The next constraint is x1 plus 3x2 plus 2x3 negative s2 plus a2 equal 4. Once x1 equal 0 plus 3 multiplied by x2, x2 equal 2 over 3 and plus 2 multiplied by 1 negative 0 plus 0 equal 4. Proved. And z equal 20x1 plus 30x2 plus 16x3. x2 equals 0. 20 times 0 plus 30 times 2 over 3 plus 16 over 1 is 36. And that is okay. It is proved. It is proved. Let's see the second example for pure strategy. Given as usual two players, player A and player B. Given also 4 columns and 3 rows. That means player A has 3 strategies while player B has 4 strategies. Now we will start with the row minimum. To select the minimum value in each row. Row number 1, the minimum value is negative 5. Of course, negative 5 more than 3, less than 3, less than 1, and less than 20. For row 2, the minimum value is 4. 4 is less than 5 and less than 6. For row 3, the minimum value is negative 6. The maximum of all these minimums is 4. 4 in this case is called maximin. Maximin, the maximum of the minimum. Okay. Now let's move to column maximum. Now we have 4 columns. The maximum value in column 1 is 5. The maximum value in column 2 also equal 5. The maximum value in column 3 equal 4. The maximum value in column 4 equal 20. Okay. So the result of this operation is that maximin equal 4 equal minimax equal 4. This is the condition of the saddle point. The condition of the saddle point is maximin equal mini max. Okay. Now let's indicate the saddle point. Inside this rectangle, we indicated 4 as game value, because this is a common value between minimax and max min. The place of or the cell in which the game value is placing is known as the saddle point. Saddle point. The place row 2 and column 3. We can call it P23. P23. 2 denotes row number 2 and 3 denotes column number 3. So accordingly, the optimal strategy for each player is, for A is 2. What that means? That means player A will play the strategy number 2 and he will ignore the remaining strategies 0, 1, 0. He will ignore first strategy and the third strategy. For player B, the strategy is 3, column 3. That's why he will ignore column 1, column 2 and column 4. In case of pure strategy, the saddle point exists all time. Put into account this remark. In case of pure strategy, the saddle point exists all time. We don't need this condition in the mixed value. Mixed value doesn't require this condition, but pure strategy requires saddle point all time. So this is a pure strategy. Example number 2, please. Nash equilibrium, new look. Find the pure strategy of Nash equilibrium in the following game, in which player 1 had 3 strategies T, M and P, while player 2 had 3 strategies L, C and R. The matrix is shown as below. Now let us arrange the impact of the choices of player 1 on the choices of player 2. If player 1 chooses strategy of T, so the strategy of T in the first row, so then player 2 will take the highest outcome. Now the strategy now is focusing on row T. If player 1 chooses T strategy, let us see what the reaction of player 2. Player 2 will choose the highest outcome in the T row. The highest outcome for player 2 is 2, R2 in the column R. Okay, let us move to the second choice of player 1. If player 1 chooses strategy of M, let's move to the M row. If player 1 chooses M strategy, then player 2 will look for the highest outcome in this row. The highest outcome for player 2 is 4. It is under the L column. It is under the L column. Okay. Now, if player 1 chooses strategy of B, then player B will choose strategy of L, because column L gives player 2 the highest outcome equal 3. Okay, that's finished for player 1. Let's move to the strategy or the campaign of player 2. If player 2 selects strategy of L, the first column, the strategy of the first column, if player 2 chooses L, then player A also will choose the highest outcome, 3, or he will choose M strategy. If player 2 chooses C strategy, then player A will look for the highest outcome equal M and T. If player 2 selects R strategy, in R strategy, player 1 either to select 4, 2 or 3, but the best outcome is 4. The above strategies shows that the common cell between the two players are 4, 2 and 3, 4. 4, 2 means strategy T, a combination of strategy T and strategy R. The next combination is 3 and 4. This combination means strategy M and strategy L. This matrix shows that Nash equilibrium has two options, TR and ML, or 4, 2 and 3, 4. Example 5. A carpenter makes 3 types of cabinets: provincial X1, colonial X2, and modern X3. The provincial model requires 8 hours for fabricating, 5 hours for sanding, and 6 hours for staining. The colonial model demands 6 hours for fabricating, 4 hours for sanding, and 2 hours for staining. The modern one takes 5 hours for fabricating, 2 hours for sanding, and 4 hours for staining. The carpenter has 96 hours for fabricating, 44 hours for sanding, and 58 hours for staining. The expected profit margins are $38, $26, and $22 on X1, X2, X3 respectively. Express the data in mathematical form suitable for finding the optimal output mix. Okay. Now we have 3 decision variables, which are X1, X2, and X3. X1 stands for provincial, X2 stands for colonial, and X3 stands for modern. So the provincial model requires 8 hours for fabricating, 8 hours for fabricating, and 5 hours for sanding, and 6 hours for staining. Now, example tells us that there are 3 decisions variables and 3 phases of production: fabricating, sanding, and staining. Now, the available time for producing a certain quantity of X1, X2, and X3 at the first stage or stage of fabrication is 96 hours. The total time for sanding is 44 hours, and the total time of staining is 59 hours. Example 5 gives $38 at a profit of 1 unit of provincial, $26 for colonial, and for Madryn is $22. That means the coefficient of x1 is 38, and the coefficient of x2 26, and the coefficient of x3 is 22. Now we need to express the data in mathematical form suitable for finding the optimal output mix. So once we are talking about the optimal output mix, that means a linear programming model. Of course, the problem is about profit maximization. Let us design table for example 5 in order to help us construct the linear programming problem. This table consists, of course, of 3 decision variables, x1, x2, x3, and the first column consists of 3 processes: fabricating, sanding, staining, and the profit. The last, from the right hand, the last column from the right hand is about the time available for producing not for the time available for each process. For example, for fabricating, the plant has only 96. For sanding, the plant has only 44 hours, and for staining, the plant has only 58 hours. Now, according to these informations, we are going to formulate the linear programming problem for example 5. A summary of the general relationship between primal and dual LPP is given in the following table. If primal objective function is to maximize, then dual objective function is to minimize. If primal objective function is to maximize, then dual objective function is to minimize. If primal variables x, j, then dual constraint is j. If primal constraint I, then dual variables y, I. If primal variables x, j unrestricted in sign, then dual constraint j is equal type. If primal constraints I is equal type, then dual variable xi is unrestricted in sign. If primal less or equal type constraints, then dual is more or equal type constraints. If primal xj are restricted in sign, then dual guess constraint is an equation, and that is example 2. Please again copy the givens and table to follow the instruction and steps of solution. Max z objective function equal x1 plus 3x2 subject to x1 less than 5, x1 plus 2, x2 less than or equal 10, x2 less or equal 4. The non-negativity condition, of course, x1, x2 more or equal 0. We are looking to solve this using simplex methods. The first step is to convert the constraint to the standard form. So the first constraint will be x1 plus s1 equal 5. The second constraint will be x1 plus 2 x2 plus s2 equal 10. The last constraint will be x2 plus s3 equal 4. z0 or objective function should be 0 equation. Then z minus x1 minus 3x2 equals 0. Design the primal table by inserting the coefficients of all variables. As you look, the first row, upper row, consists of non-basic variables. The second stands for S1. The third stands for S2. The fourth stands for S3, and the last stands for Z or objective function. The row number 1 or the row S of S1 consists of the coefficients of x1, x2, s1, s2, s3 and solution in the first constraint. Return back to the first constraint where the coefficient of x1 is 1, there is no x2, then the coefficient equals 0. There is s1, the coefficient is 1, there is no s2, s3 respectively equals 0, 0. The solution is 5. The second constraint is x1 plus 2 x2 plus s2 equal 10. So the values of s2 is 1, 2, 0, 1, 1 and 10 as solution. S3 consists of x2 and s3 and solution only. Here there is no x1, there is no s1, there is no s3, s2. So the contents of this row is 0, 1, 0, 0, 1, 4. Z equal negative 1, negative 3. The remains are 0. Please again copy these givens and copy the primal table in order to follow our instruction and steps in the process of solution. Otherwise it will be so difficult to understand the solution of this problem. Based on the above mentioned rules, entering variable x2, leaving variable S3, pivot element 1. Pivot equation is 0 1 0 0 1 4, and the values of x n in the next table. Now let's follow the impacts of entering x2 as basic variable on s1, s2 and z. The result of calculation gives that the new s1 is 1 1 1 0 1 0 0 5. The new s2 is 1 0 0 1 negative 2 2, and the new z is negative 1 0 0 0 3 and 12. The last new z shows that we need to design next table, because still we have negative value here. We mentioned before, we reach the optimal solution when the negative value in the row of z will disappear. So we need to design table to avoid the negative values. That we are going to do. The second table is given as, let's check that x2 replaced s3, x1 is new entering variable, s2 is leaving variable, the pivot is 1, pivot element is 1, pivot equation is 1 0 0 1 negative 2 1, and this will be the values of x1 in the next table. So how we determine x1 as entering value? Because it faces the negative value in the row of z, which is negative 1, only one negative value. Okay, and we determined s2 as leaving variable because 5 over 1 is 5, 1 over 1 is 1, the result is 1, then s2 is leaving. So as you see, s1 will stay as valid variable, s2 and s3 will equal 0 in the last version. We will get s1, x1, x2 and z. The entering of x1 as a basic variable will impact on s1, x2 and z. The new s1 will be 0 0 1 negative 1 2 3. The new x2 will be 0 1 0 and 4. The new z will be 0 1 1 and 14. 1 1 and 14. Now we are going to design the last table. Okay, pay attention to the table number 3. We reached optimal solution because there is no negative negative values in the row of Z. But let us read the values of this table. S1 equal 3. Check the last column on the right side, the column of solution. S1 equal 3. There is no S2 and no S3. That means S2 and S3 equal 0. X1 equal 2. X2 equal 4. Z equal 14. Let's prove our findings. Now, if refer to standard form, x1 plus s1 equal 5, x1 equal 2, s1 equal 3, it is 5, proved. The next constraint, x1 plus 2, x2 plus s2 equal 10. There is no s2 equal 0. x1 equal 2, x2 equal 4. 2 times 4 equal 8. 10, proved. x1 plus s3 equal 4. 4 plus 0 equal 4, proved. Z equal x1 plus 3 x2. Z equal 2 plus 3 times 4 equal 14. Then, to maximize profit, firms should produce 2 units of x1 and 4 units of x2. The optimal solution within given constraints. This, please recheck these 2 problems. If any questions, reply please using the various social media.